Okay, this is conceptuality13b, and we're going to deal with these triangles. I just wanted to show you some dynamics of the triangle that are just really really interesting and rational, and cause you to consider the characteristics of the triangle as actually a computing tool. I'm just going to show you in general terms right now with this demonstration. We have starting with this triangle, it's a 5, 3, 4 triangle, which just happens to be a right triangle. And I just wanted to show you, we know that if we have a triangle, that if we keep the height the same and the base the same, the area stays the same. Okay, so this 3, 4, 5 triangle has an area of 6. You can get that with the side calculation, even from Google, side computer. Okay, now so we came up with an area of 6, and so that no matter what we do here, as long as we keep this keep this height the same, where you have an area of 6 no matter what that triangle looks like. So basically what we've done is we've put a line parallel to the base, right? So that we know that we can run that vertex all the way along that line and we don't change the area. And we've done the same for the base, using 3 as the base. And we've done the same for using 4 as the base. We have our parallel line up here. Now what we end up with is a larger triangle, a 2-frequency triangle of exactly the same triangle, the 3, 4, 5 triangle, here, 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 and here, which makes this total area 4 times 6 is 24, is the total area of the big triangle. Now some really amazing things happen when we move this across the potential of this line. I have it marked off here in the same frequency as the base, so it stops here, it stops here, it stops here, it stops here. But really it's a continuous movement. So how do you decide what the frequency is when you have continuous computation going on like this? You have area being lost from this triangle and adding it to this triangle, until finally you get over here and you have two new triangles with an area of 6. So it's fascinating that you can have all these different shapes with exactly the same volume, and the triangle is computing that just naturally. We can move over here and show it to you from another side. Here we have the triangle, and I put now we have the frequency 3 base, right? So I have put 3 stops here. This removes 1/3 of it. This removes 2/3 of this one, and adds 1/3 to this one, and then finally you have the right triangle where you have 6 here and 6 here. And all of that stuff is happening simultaneously. The subtraction and the addition of taking the areas out of this background triangle while leaving the triangle that we're dealing with constantly of the same area. And then we'll be using this concept later on also. But this is just the nature of triangle, and it's awesome. Now in this case, the 5, 3, 4 happens to be a right triangle. So for the 3 side, the 4 is height, and for the 4 side, the 3 is height, right? So I've made a more complicated triangle here. That this isn't a right triangle, but it does all the same things. In this case, we know the area by the side formula is 9.92, so we know we can get the height. 19.84 divided by 6 gives us the 3.306 height here. We turn it over here, and we have the same thing, the 19.84 divided by 4, which gives us a 4.96 height. And we can do turn it to the 5, and we have 1984 divided by 5, and that gives us the 3.968 height. So calculating all those heights, we do end up with exactly the same 9.92 area, looking from all those different perspectives. And here we can turn this triangle right here by dividing the 6 into 3, just having it going vertical with our a height vector, and we have an equilateral triangle, and these would be two right triangles, each with the area of half of that. And then we can move along. We have the same frequency up here, and we can just move along, vector by vector. But we are not changing the base, but we are changing the relative the length of those sides. And those sides are just, they're changing as we move this along, right? But once we stop, we can calculate what areas are left in here, and what areas left in here. But we know this area is always the same, 9.92. So I just wanted to show you that, and we'll review with another video and with some other diagrams.